All right, welcome back, class, to chapter 13. In this week, which is a shortened week because of Labor Day, we're going to cover the rest of chapter 13, which is part 3 and part 4. All right, so part 3, the focus of this video is going to be three things. The integrated rate law, of which there are three kinds. There is zero order, first order, and second order. And we're going to talk about where these equations come from. And based on these integrated rate laws, they can be simplified into half-life equations where t of 1/2 is equal to various things, again, based on the derivation from the equation. And then from the integrated rate laws, they can actually be plotted in a straight line formula or a straight line plot. And we're going to talk about looking at these graphs at the very end of this video. If you have time, I would stop the video right now, or pause the video, and go ahead and write these six equations down. There are three integrated rate law equations, so this is one of them. This is for zero order. This is for first order, and this is for second order. Okay, these are called the integrated rate laws. Okay, I would also write these equations for the half-life, and when you have zero order, the equation becomes for the half-life t 1/2, and the 1/2 is subscript. Okay, so really it's t and then 1/2 like that. Okay, is equal to this, and then this is for first order, second order. So you've got zero order, first order, and second order. Okay, and then last but not least, for the straight line, I would write that for zero order you have concentration of A versus T. For first order you have ln of concentration versus T, and for second order you have 1 over concentration of A versus T. And don't forget, when we say zero order, first order, and second order, what we are really referring to is when we have the rate law. Rate equals K times the concentration of some substrate, which is a reactant. It is raised to a power. It could be 0, it could be 1, it could be 2. Okay, whatever is this power, it could be 0, it could be 1, it could be 2. That is what we're talking about when we say zero order, first order, and second order. Okay, so the rate changes over time. Thus far, we have examined, especially in the last section of videos, how to determine the average and instantaneous rate expressions. Remember, we said that the rate is always equal to the change in the concentration over the change in time. Okay, and so with this equation, what it's saying is that as time progresses, the concentration of your substrate, whether it's the reactant or the product, will change. And so from those, we have some rate laws, right? And we said the rate laws are rate equals K, some rate constant, okay, times the reagent A, reagent B, so on and so forth, okay? And remember, these must all be reactants, okay? We talked about a rate constant and how to calculate the rate constant K. And we said that for these kind of rate laws, we have these rate orders, right? The rate orders are going to be M, N, and P, and we learned how to solve for these in the last couple of videos, okay? Now, all this information that we've talked about so far applies to concentration of the substrate at a particular moment in time, okay? So we have these graphs that we're going to show you in just a second, okay? And basically, it is happening, and we're taking a snapshot and saying, this is the concentration at this set time, okay? But really, we would like to know or be able to examine a mathematical function that expresses how the concentration changes over a particular period of time, okay? Because we would like to be able to say, at the beginning of the reaction, there's this much material. At this middle of the reaction, there's this much material, and at the end of the reaction, there's this much material, right? So another way of saying that is if you have this graph here where you have concentration on your y-axis, and then you've got time on your left x-axis, okay? Before, we were just saying, okay, what is the rate from this time to this time? And we learned how to calculate that, right? We said that you have, like let's call this y1, let's call this x1, call this y2, x2. We said, all you have to do to find the rate is you say y2 minus y1 over x2 minus x1. And you did this in the beginning at the chapter. You said, what is the concentration over the time, right? And you found the rate at this little interval or this little interval or this little interval, okay? But the integrated rate law tells you or allows you to calculate what is the concentration at any of these times with one equation, okay? So the way we do this is we actually do a little bit of calculus. We say an integrated rate law can be determined because we know that the rate is equal to the change in A over the change in time. It is negative if it is a reactant. And since when we're looking at rate laws, we're looking only at reactants, we're looking at it as a negative, okay? And so we're going to integrate here from the concentration of AT to the concentration of A0. And we're going to integrate here from T to 0, okay? So basically we're integrating from time 0 to time t, okay? Time t meaning whatever is the time during the reaction. This, if you do the calculus all the way through, and if you would like to see how that is done, you can look in the book. The book walks you through it in the margins, okay, of your book. You end up with this equation, ln of A of t over A of 0 equals minus kt, okay? A of t, this thing here, tells you what is the concentration at time t, okay? And t can be, 10 seconds, it can be 100 seconds, it could be 500 seconds, wherever it is in terms of your progress in the reaction, okay? A of 0, and this 0 stands for initial, or time 0, okay, means that this is the concentration at the beginning of the reaction. Let me rewrite that again clearly. It is at the beginning of the reaction. Another way of thinking about this is how much you've added to the reaction flask at the beginning, okay? So if you have the rate constant K and the initial concentration, which you should have because if you started the experiment, you should know how much you added at the beginning, you can determine the concentration at any given time, okay? The concentration at any given time is A of t using the integrated rate law, okay? So basically, although the rate is changing over time, and this is the rate, this is the slope, right? The slope of this line is the rate. So the rate at time t, at T1 versus T2 versus T3 is changing. Okay, but using this equation, okay, you should be able to calculate what is the time at all of these intervals. And this is only for first order, okay? There is an equation for each of the other orders. It requires a little bit of calculus to run them all through, okay? For second order, we have this equation here, okay? And the reason is that it's different is because now we're integrating, and there's a squared here, so we're integrating again, same thing, from A of t to A of 0, and then from 0 to t. But because this is squared, that once you integrate it, it becomes very different. It is 1 over A of t equals kt plus 1 over A of 0. And again, this concentration with the subscript of t stands for the concentration at time t. And this concentration A with a subscript of little 0 stands for the concentration at time 0, which is the beginning of the reaction. Okay. Last but not least, if you do the same integration on a 0 order, and again, the only difference here is now this is 0 instead of 1 or 2, you get this expression where you get A of t equals minus kt plus A sub 0, okay? Now these three equations here that I've circled are really just these three equations here, okay? These three equations here that we talked about and I asked you to write down, okay? And if you have these written down, it'll be very helpful, especially when you're doing quizzes and exams, because then you don't need to try and fiddle around finding these equations, okay? So let's take a look at how we would use these three equations, okay? So let's read the problem here. Example 13.5 from your book says that the decomposition of N2O5 to NO2 and O2 is first order. It's very important that you pick up that it is first order, okay? So what they're saying is that it is rate equals K, N2O5 is to the first order, okay? And it has a rate constant of this, okay? Rate constant is K, right? At 45 degrees. So if the initial concentration is this, 1.65, remember the initial concentration is always written as, and remember the initial concentration always has this little 0 here, okay? What is the concentration after 825 seconds? This is obviously T, right? So pulling this information, we say here, this is the rate constant. This is the initial concentration. This is time, okay? And they would like you to solve for what is the concentration at time t, right? So you're solving for concentration at time t, okay? We have all of this. We're using this equation here because it is first order, okay? So let's solve this equation. We're going to say, and we're going to plug in everything we know, ln. And I would usually like to put these large parentheses here so I don't separate the fraction on accident, okay? We don't know what N2O5 at time t is. That's what we're solving for. We do know the initial concentration is 1.65 times 10 to the minus 2 molar, okay? Equals minus K is 4.80 times 10 to the minus 4, 1 over seconds. And my t is 825 seconds, okay? My seconds do cancel out, okay? Simplifying this equation, all of this is equal to minus 0.396, okay? So if you put it in your calculator, that's what you're going to get, okay? So now really it's ln of all of this equals minus 0.396. How do I get rid of the ln? Okay, the opposite of ln is e. Opposite of natural log is raising it to the e. And if you have a graphing calculator, okay, the e is above the natural log. So if there should be a button on your graphing calculator that looks like this. Okay, if you look above it, there's a little thing that says e to the x. Okay, so really if you're using a Texas Instrument graphing calculator, you're going to hit second and then this button. So you're going to hit first, you're going to hit this thing here, like looks like this. It's in the upper left hand corner of your calculator, followed by hitting this button. Okay, so you're going to hit this button followed by this button to get the e. Okay, if you do e to one side, you're going to do it to the other side. So this cancels out. So really this becomes N2O5 to the t over 1.65 times 10 to the minus 2. And e to the minus 0.396 is equal to 0.673. Okay, we're going to multiply this side by 1.65 times 10 to the minus 2 molar. We're going to multiply this side by 1.65 times 10 to the minus 2 molar. Okay, that cancels that out. So really N2O5 at time t, or the concentration of N2O5 at time t, is going to be equal to 0.0111, or I would like to write it in scientific notation, 1.11 times 10 to the minus 2 molar. Okay? and check. Make sure that your answer makes sense. You started off with 1.65 times 10 to the minus 2. You should have less as time progresses, right? This is a reactant, so it should decrease. So 1.11 times 10 to the minus 2 is indeed less than 1.65 times 10 to the minus 2. Part B says, I'm going to draw a line just to separate these two things. Part B says, how long would it take for the concentration of N2O5 to decrease to 1.00 times 10 to the minus 2 molar? So again, we know what K is. K is given above. Okay, but now, and the initial concentration stays the same, right? So these two things are the same. Okay, so under no, your K is still 4.80 times 10 to the minus 4, 1 over seconds. And your initial concentration is 1.65 times 10 to the minus 2 molar. Okay, what has changed is now they want you to solve for T. They say, how long would it take? Okay, and they want to know how long it would take to get the N2O5 concentration to 1.00 times 10 to the minus 2 molar. Okay, so again, we're just going to solve. Okay, we're plugging it into that same first order equation, ln, and we're going to go 1.00 times 10 to the minus 2 over 1.65 times 10 to the minus 2, okay, equals minus, K is still the same, 4.80 times 10 to the minus 4, 1 over seconds, and you're doing T. You're solving for T, okay? So really we're going to divide this side by negative 4.80 times 10 to the minus 4, 1 over seconds. And we're going to divide this whole thing, okay, by minus 4.80 times 10 to the minus 4, 1 over seconds. So if you solve all of that in your calculator, okay, the top part is going to be minus 0.501 over minus 4.80 times 10 to the minus 2, 1 over seconds, okay, equals, this cancels out, you have T on this side, and if you solve all of this, okay, that's going to give you 1.04 times 10 to the third seconds, okay, so that's your final answer there. Okay. So it's going to take you about 1,000 seconds, okay, to convert 1.65 times 10 to the minus 2 molarity to 1.00 times 10 to the minus 2 molarity. Okay, this is for a first order reaction. I'm just going to do one more because I do feel like it's important to understand how to solve these equations. Okay, so the next one says the decomposition of N2O5 to N2O2 is first order. Did I repeat this question? I did it twice. So this question is the same as this question, so I accidentally had the slide twice. So just skip the slide because that's the same slide. Let's go over to this question here. All right, so it says you have 2NOBr becomes 2NO plus Br. The reaction is a second order reaction with respect to NOBr. Very important to pick up that it is second order. Because it is second order, oh, this is a typo here. Because it is second order, okay, it should be this equation here that you're using, okay? So it says that the rate constant is this. Rate constant is K, right? So the rate constant is 0.810, 1 over M, 1 over S, okay? The initial concentration is this. The initial concentration is 7.5 times 10 to the minus 3. That is this thing here, right? Remember we said if it has a little subscript 0, it's the initial. Okay, and they would like to know how much NOBr is left after the reaction time of 10 minutes. So they want to know what is this at time t. T is 10 minutes. Okay, very important to take note here that because your K is in 1 over seconds, you need to convert time into seconds. Okay, so let's do that real quick. We know that 1 minute is 60 seconds. So that really 10 minutes is 600 seconds. Okay. So now that you have everything under no, let's solve. Let's do it in black, so because I'm used to doing it in black ink. So we're going to go 1 over the I'm going to start, let's see, 1 over, what are we doing? NOBR, okay, to the T, okay, is equal to, and the K is 0.810, 1 over M, 1 over S, okay. This time is 600 seconds, okay, plus 1 over 7.50 times 10 to the minus 3 molar, okay. So I'm solving for 1 over N over BR. So if I do all of this in my calculator, I'm just going to write the number down. I get 619.33, okay, and I'm just bringing this down here. Okay, so I have 1 over the concentration of NOBR at time t, but I don't want that. I want just concentration at time t. So how do I get rid of the 1 over, or how do I bring it to the top or the numerator? I really need to do the reciprocal, okay? So I need to take this and do the reciprocal, and take this and do the reciprocal, okay? When I do that, I end up on this side with concentration of NOBR at time t equals 1.61 times 10 to the minus 3m, okay? And again, you would like to make sure that your answer actually makes sense, okay? You started off with 7.5 and you're ending up with 1.61. That makes a lot of sense. It makes perfect sense. The other thing I would like to say is, how do you do this reciprocal? The easiest way to do it is to take this and do the little hat to the minus 1. So you just write 619.33, and then you press the little, what do they call it? The button looks like a little hat, like that, and then -1. Okay? So that's how you would input that into your calculator. All right. Part B says, how long would it take for the concentration to decrease to 1.00 times 10 to the minus 3 from its initial value? And again, this is very similar to the one we just saw, and basically the K is the same. The initial concentration is the same. The only difference is now they're telling you NOBR at time t, which is going to be equal to 1.00 times 10 to the minus 3 molar. And they would like you to know what is the time, or solve for how long, right? So now you're just going to solve and plugging it into the same equation you've been using, 1 over, and now your A of t, you know what it is. It's 1.00 times 10 to the minus 3m is equal to K, which is 0.810, 1 over m, 1 over s. And instead of 600 seconds, you're now solving for how long, plus 1 over, and this is your initial concentration. That has not changed. Okay, to solve this, we're going to make this whole number. So this is 1,000, okay? I'm bringing down the 0.810 and the t, and I'm going to simplify this thing. This thing, if you put it in your calculator, it comes out to 133.3. I subtract 133.3 from both sides. Okay. Sorry, this is 1 over m. Okay. So that comes out to 866.7, 1 over m, okay, equals 0.810, 1 over m, 1 over s, times t, okay. Divide both sides by 0.810, 1 over m, 1 over s. We divide this side by 0.810, 1 over m, 1 over s. The 1 over m cancels out. This comes out to, if you do that on your calculator, I'm going to write it here since I'm running out of space. 1.07 times 10 to the third seconds equals t. Okay, this cancels out. So I've got t equals, and this, all of this comes out to this right here. Okay, and if you wanted to, you could convert this into minutes. This is approximately 17.8 minutes. Okay, all right. So hopefully you have a good idea of how to use these zero order, first order, and second order equations, okay, and how to do no solve for this. I really suggest you do no solve. And as you're reading the problem, it's good to highlight what order you're using, so you know what equation you're using, and to write like the k is the rate constant and things like that. Okay. All right. Now from this, we can do something called half-life. And half-life, the variable is just t to the 1/2. That's this variable here. Okay. The time it takes for the reactant concentration to decrease to 1/2 of its initial concentration. So on this graph here, you started with 0.165 moles per liter at time 0. Okay, so that's this at time 0. Okay, and half of this amount, 0.0165, is 0.0083. Okay, and it takes, according to this graph, over 1,000 seconds, about approximately 1,000, almost 500 seconds. Okay, so this is what we call the half-life. The half-life is the time it takes for the concentration to decrease by half the amount. Okay, and again, they have like, if you have two half-lives, it means that it's decreased to another half the amount, and this is called 3 half-lives because it's decreased to 3 halves of that amount. So basically you have like t 1/2, right, is really this time here. Okay, another half-life, so on and so forth. Okay, so really what we're saying is that what half-life is that your concentration is 1/2 of your starting concentration, right? When at t 1/2, okay, your concentration is half of what you started out with, because A of 0 is what you started with. Okay, so this is the equation that we're going to use moving forward. We're going to plug it into our integrated rate law. Okay, so looking here, your integrated rate law for first order is ln of A, concentration of A at time t divided by concentration of A at time 0 minus kt. What we're going to do is, instead of writing this, okay, we're going to write 1/2 A0, because A of t at the half-life is half of the original amount. So that's exactly what we have here. We've plugged that in here. Okay, and notice when you do that, you can cancel out the two A of zeros. This simplifies it to ln of 1/2 is equal to minus k, and t is not t, t is t 1/2. Really, it just means it's a variable. The 1/2 is not multiplied or anything like that. It's just t at 1/2. Okay, it's just like when you did rate 1, this just means experiment 1, right? So this 1/2 just means when half of your reactant is gone. Okay, that is not actually used in any of the calculations in terms of an actual fraction. Okay, so if you do that, okay, you can actually divide this side by k minus k, divide this side by minus k. ln of 1/2 is actually negative 0.693. So really your equation for half-life simplifies to t 1/2 is equal to 0.693. Okay, we can do that for second order. Same thing, where we have t 1/2, we're going to plug in 1/2 A of 0, and again, that's what we did here. Oh, my Apple Pencil is getting low. So really, if you do this, we're going to multiply both sides by 1 over A of 0. We're going to do that to this side. You're going to multiply by A of 0 I'm going to just erase this so I can just write a little bit more clear here. Multiply this side by a of 0. Multiply this side by the same thing. Okay, this cancels out. You get 1 over 1/2, which is basically 2. Okay, and this distributes in. Okay, this times this becomes 1 over 1, or 1. Okay, and becomes a of 0 times k times t 1/2. Okay, you're going to subtract both sides by -1, get rid of this. 2 minus 1 is 1. Okay, and so if we divide this side by k a of 0, divide this side by k a of 0, the k cancels out, the a of 0 cancels out. I'm left with t 1/2 is equal to 1 over k a of 0. Okay, and last but not least, oops, I jumped screens again. For 0 order, okay, we're doing the same thing. We're plugging in here 1/2 a of 0. Okay, all I've done to simplify this equation is I'm going to subtract a of 0, subtract a of 0. So I get 1/2 of a of 0, and I have kt to the 1/2. I divide both sides by k, and I end up with this equation here. And again, these three equations, this one, and this one, was in that first slide that I covered. Okay, so really, let me just go through quickly an example of how you would use these half-life equations. Okay, it says sulfuric chloride is a colorless corrosive liquid. It's first order reaction. Okay, so at 320 degrees Celsius, the rate constant, this is 2.20 times 10 to the minus 5, 1 over s. And they want to know what is the half-life at this temperature. So because it is a first order reaction, okay, we're going to go back and we're going to use this equation here. Okay. So using that equation, okay, which I've got written for you, okay, and we have k equals, 2.20, and it is first order, so we're using this equation. Okay, so we're going to plug that into k, and that's exactly what I have here, 0.693 divided by 2.20 times 10 to the, it should be up high, -5. I get 3.15 times 10 to the 4th seconds. B says, how long would it take for 50% of the SO2 Cl2 to decompose? So 50% really, if you convert your 3.15 times 10 to the 4th into hours, that is your half-life. It is 8.75 hours. The other way to do it is to do the integrated rate law, okay, and you're just plugging in. You start off with 1 molar, half of that is 0.5. If you do that all the way through, you're still going to get the same thing, 3.5 times 10 to the 4th, and that converts to 8.75 hours, okay? And the way to convert from seconds to hours, I hope you know how to do that. If not, you should find me in office hours. Part C says how long for 75% of it to decompose, okay? For 75% of the decompose, if you start off with 1 molar, 75% less is 0.250, okay? Hopefully we can do that math really quickly in our head. And again, we're using our integrated first order rate law equation, and we're going to plug in our A of T and our concentration at 0. This is equal to minus K times T. And so solving all of that through, okay, T would equal 6.3 times 10 to the 4th. And we should convert that seconds into hours, 17.5 hours. Okay, this is very much a review of what we just covered at the beginning. Okay, last but not least in this little video is that these integrated rate laws can actually be graphed in a linear way. Okay, so for first order, you have ln of A, the concentration of A at time t over A at time 0 equals minus kt. This actually simplifies to ln of A of t minus A of 0 because ln of x over y is equal to ln of x minus ln of y. This is a basic natural log equation that we should know from math. Okay, so all we're going to do is we're going to move this to the other side. So we're going to add ln a of 0, and we're going to add that to this side. Let me rewrite that clearly. Okay, this cancels out. Really, I end up with ln a of t equals minus kt plus ln a of 0. Notice that this is my y, t is my x, okay, and this is my y-intercept, okay. So graphing that, my y-axis would be ln of the concentration of my reactant, and my x-axis would be time, okay, and that's basically what we've done here. Okay, and it is in the form of y equals mx plus b. Notice that the slope is negative k. Okay. This is for first order. Okay. For second order and for zero order, it is already in the form of y equals mx plus b. No rearrangement necessary, because your y is your 1 over a of t. Okay. Your k is your slope. And your y-intercept is 1 over a of 0, and your t is your x, okay? So basically what we're doing is, and we're going to do this in the Lab 3 lab that you're going to watch a video on Canvas. Basically, we're going to do a reaction, and we're going to plot the concentration over time, okay? Now, you're going to plot it 3 different ways. So basically what you're going to do, I'm just going to scroll so that I have a little bit more space. You're going to graph the concentration. Let's call that A over time. You're going to take that same data of concentration and graph it as ln, or natural log of the concentration over time. And then you're going to graph it one more time as 1 over the concentration over time. Okay, and what you're going to get is you're going to get 2 graphs that look like this, okay, and 1 graph that looks very much like this, okay. And the nice thing about this is if you fit it, okay, what's going to happen is you're going to try and, the computer is going to try and fit it and make it a line, okay. And you can see that the first one and the last one is more of a curve than a straight line. So this is actually not a good fit. Okay, or not the best fit. Neither is this one. Okay, but this one matches up fairly well because the lines overlap very well. The overlap is good. So very much so we say this is the best fit line. If that is the case, then it's not zero order, it's not second order, it is first order. Okay? And so that's really what we mean when we say, and at the very, very beginning, right, we had these 3, where is it now? At the very, very beginning, we had these 3 things. We said zero order is A versus T. First order is ln of A versus T, and second order is 1 over A versus T, okay? So because of that, based on the order, we should be able to figure out what is the M, N, and P. M, N, P, yeah, okay? So again, your book just shows you an example of what is a good fit versus a bad fit, or not so good fit. So here you can see here the teal line is the curve that you've plotted with your actual points, and then the computer program tries to straight fit a line to it, and you can see it doesn't overlap very much or very well. Whereas if you have a very good overlap like here, where it's just perfectly straight, that is the best fit. That's why this has this thing here, but this has a star here because this is a very good fit. Okay, so based on this data, you would say it's not ln of NO2. This is ln is the first order, and 1 over A is the second order. In this example, you would say the second order is the best fit. Okay, in this example that I gave you here, let me just scroll here. In this example, because ln of A is the best fit, then it is first order. Okay, so it helps you to solve for M, N, and P. Okay, so your book has this table here. I like that this table basically is a repeat of that first table that I gave you. Okay, I like that table in the beginning better, but again, you can use this table or that table. It gives you the exact same information. It gives you the rate law, okay, for 0, first, and second order, okay. It gives you the integrated rate law. It gives you the half-life equations. If you're going to use this table, you have to know that this is equal to T1/2 equals T1/2 equals T1/2. And of course, this is your straight line plot, X and Y axis. All right, I'm going to stop the video here. I would go ahead and do your homework on the integrated rate laws and half-life. There's one more video after this on chapter 13. So I'm going to stop this video here.